Hello students, this is Dr. Ruchira Choudhury and today I am starting the second chapter of Theory of Probability. The first chapter, that is the link of the first chapter, is given in the description box, so you can find my first chapter if you have not seen my first video. So let's start. So before we go to some more theorems of probability, we will have to learn about two important terminology, that is mutually exclusive and exhaustive. So at first, mutually exclusive. The events are said to be mutually exclusive when two or more events cannot occur simultaneously, like tossing of a coin. In that case, either we know that in case of tossing of a coin, we know either head or tail will occur. But it is impossible that head and tail will occur simultaneously at a time. So, tossing of a coin is the example of mutually exclusive event. Now, I am coming to the definition of exhaustive events. Several events are said to form exhaustive set if at least one of them must necessarily occur. So these are the two important terminology. Now I am going to the theorem of total probability. Now I am coming to the theorem of total probability. If two events A and B are mutually exclusive, we have already known about the event mutually exclusive. The events are said to be mutually exclusive when A and B, the events A and B cannot occur simultaneously. So, if two events A and B are mutually exclusive, then the probability of the occurrence of either A or B is given by the sum of their probability, that is probability of A plus B is equal to probability of A and probability of B. So, this is the probability of A plus B. This means the probability of the occurrence of either A or B, and this will be equal to probability of A plus probability of B. Now I am coming to the theorem of compound probability. This is like that: the probability of the occurrence of the event A as well as the event B, that is the probability of AB, that is the probability of the occurrence of the event A as well as the event B, is given by the product of the probability of A, this is, and the conditional probability of B, assuming that A has actually occurred. This is the conditional probability of B assuming A has actually occurred. So this is denoted by probability of B divided by A. So conditional probability of B assuming A has actually occurred, this is denoted by P of B divided by A. So conditional probability of A when B is actually occurred, B is already occurred, is denoted by P A divided by B. And this formula can also be written as probability of B dot probability of A by B. So this is the theorem of compound probability. By the way, I suggest you to read the chapter of set theory in order to understand clearly the theorem of probability. So the link of the playlist is given in the description box. Please find it and read thoroughly the chapter of set theory before going to learn the theorem of probability. So we have learned about two theorems. This is the theorem of total probability and this is the theorem of compound probability. And this theorem holds only when A and B are mutually exclusive events. When A and B are not mutually exclusive, then this formula becomes probability of A plus B equals probability of A plus probability of B minus probability of AB. So when A and B are mutually exclusive events, then AB that is A intersection B will be equal to phi, and probability of phi will be equal to 0. So when A and B are mutually exclusive events, then this formula will be become this formula. So we can get this one from this one. So this formula only holds when A and B are mutually exclusive, and the theorem of compound probability is like that, and this can be also written as probability of B dot probability of A by B. And I will solve a problem related to this theorem, that is the theorem of compound probability, to understand this clearly. Now an urn contains 4 white and 6 black balls. 2 balls are drawn successively from the urn without replacement of first ball. That is, I am drawing the first ball and then I am drawing the second one. If the first ball is seen to be white, what is the probability that the second ball is also white? That is, when I am drawing the first ball, it is seen to be white. And what is the probability that the second ball is also white? Now I am assuming A1 be the event that first ball drawn is white, and A2 be the event that the second ball drawn is white. Now what we will have to find out? We will have to find out that probability of A2 divided by A1. That is, probability of A2 divided by A1 means probability of A2 when A1 is already occurred. That means probability of that the second ball is white when the first ball drawn is already white. So what is the formula of this? The formula is probability of A1 intersection A2 divided by probability of A1. Now what is A1 intersection A2? A1 intersection A2 means the common event, that is the first ball drawn is white and also the second ball drawn is also white. So probability of A1 intersection A2 will be equal to probability of A1 dot probability of A2, because these two events A1 and A2, these are two independent events. So this will be equal to probability of A1 into probability of A2. Now what is probability of A1? A1 is the event that the first ball drawn is white. So I am drawing the ball from white ball, that is I am drawing from the 4 number of white balls, and the total number of balls are 10. So this will be 4 divided by 10. And A2, probability of A2, I am drawing second time. So I am drawing from the 3 white balls, and total number of balls will be 6 plus 3, that is 9. So this will be 3 divided by 9. So this will be equal to 2 divided by 15, and we will put the value of this in this formula. So probability of A1 intersection A2, 2 divided by 15 into 10 divided by 4. So this will be equal to 1/3, 1 divided by 3. This is the answer. So this is all about today's class, and on my next class I will discuss about Bayes theorem and solve some problems related to it. So for today it's time to say bye bye.